experiment. Right. So the ingredients that we are reasonably sure exist in our universe are the following sets of cartoons. This is my mental picture of the universe as a very abstract person. So we know that we had the standard model present in the early universe in internal thermal equilibrium, at least at temperatures of order in eV when the cosmic microwave background was formed. And our earliest evidence about the state of the universe at very small scales, very early times, very high temperatures, are the successful predictions of Big Bang nucleosynthesis, which tell us to exquisite degree of precision that the standard model was there in the universe in thermal equilibrium, as best we can tell, up to temperatures roughly order few MeV. Besides the standard model, we know that there needs to be something new to be dark matter. We have excellent evidence from cosmic microwave background, large-scale structure. In addition, we're beginning to get other interesting, although less sharp kinds of information about dark matter from galaxies in the late universe. We know that we know that whatever dark matter is, it is something new. It has to walk and talk like a massive particle, and it has limited interactions, definitely with us, and even to some extent with itself. Beyond these ingredients, we also know that the cosmic perturbations that we see beautifully in various stages of evolution, from the cosmic microwave background on through galaxy formation and evolution, had to be seeded by something, either inflation or something else that does the job. And whatever inflation accomplished, you typically need to give non-gravitational couplings to whatever this inflaton is in order to successfully manage the transition into the hot radiation-dominated universe that we see evidence for over here. So if you just take these minimal ingredients and you put them together, you get a cosmology that looks something like this, as a function of the scale factor of the universe and the energy density. We can track back the dark matter dominated era. I've left the very recent cosmological constant dominated era off the plot because I'm going to be interested in way earlier times. Then around the time of the cosmic microwave background formation, the standard model radiation density was dominant, and we have an era where of radiation domination. And the minimal ingredients for the universe tell us, you just keep running this radiation domination period back. Has to go at least up through order few MeV to give us successful Big Bang nucleosynthesis. And then we don't really know what happens. There's this big question mark before you match on to reheating at some unspecified scale. So conventionally, of course, one takes this idea of radiation domination and does the minimal, intellectually conservative thing and just project this back to reheating. And that's sort of the standard history. But there are an awful lot of possibilities for what the expansion history of the universe could be before Big Bang nucleosynthesis. And it is interesting to think about what kinds of particle physics can give rise to interesting departures from radiation domination. And of course, in ways that hopefully could leave observational footprints that we would be able to go out and search for, which would ultimately let us push this something happens bar further back in time and give us more direct understanding of the very early history of our universe. So early departures from radiation domination can arise in a variety of natural ways from well-motivated models of beyond the standard model particle physics. Of course, very famously, if you have a scalar field that is evolving in a coherent way in the early universe, famously, of course, the inflaton, but very similar physics, a modulus, you have, in these cases, some scalar field that is in the early universe displaced from the minimum of its potential and coherently oscillates in its potential. This ends up sourcing a energy density that behaves cosmologically like non-relativistic matter. So when you have this kind of stuff in the early universe, it generically leads to a epoch of early matter domination that then ends, has to end to give us back the successful predictions of Big Bang nucleosynthesis, the rest of our observed cosmology, when this coherently oscillating field decays. Now, as Raymond and collaborators have developed very beautifully in recent papers, if you have a coherent scalar field, this sort of up and down radial oscillation that gives you matter-dominated eras is not the only thing it can do. It can also be born in a state that ends up giving you a period of angular motion, coherent angular motion. In that case, the kinetic energy of the field can dominate the expansion of the universe, and that gives you an epoch of kination. This is a form of energy density that redshifts faster than radiation. And something that I've been having fun thinking about is what happens when you have relic thermal baths in sectors where the lightest particle, unlike the case in the standard model, has a mass. So particle physics with a mass gap. In this case, so the kinds of theories I have in mind are where you have some hidden sector of self-interacting fields that is thermally decoupled from the standard model. This is a kind of scenario that can very easily give you dark matter in a way that very depressingly matches all of the cosmological requirements for what dark matter needs to be, while giving you essentially zero terrestrial detection hope in a wide range of models. These kinds of models are depressingly easy to construct in top-down theories such as string theory, which like to give you self-interacting hidden sectors in addition to the standard model, often reheated at different temperatures and out of thermal contact with the standard model. And so I've been interested in trying to think of ways in which one could go after observational footprints of thermally decoupled hidden sectors. And one thing that a thermally decoupled hidden sector can do that doesn't happen in the standard cosmology is when the lightest particle in the hidden sector is massive, well, here you have a particle as massive with a thermal number abundance. And this is generically something that can come to dominate the energy density of the universe. Just like a modulus, it will give you a period of early matter domination up until this particle, which has to be metastable if this is going to be an acceptable cosmology for our universe, then decays, which ends the early matter dominated era. This is a period of reheating. It's not post-inflationary reheating, but it is the decay of something into the standard model that gets us back onto the standard radiation dominated cosmological history. So I'm interested in seeing whether we can use the departure from the standard radiation dominated cosmology as a potential way to get a handle on the energy content of the early universe prior to BBN. So the tool that we're going to use is the growth of density perturbations during this pre-radiation domination epoch of altered expansion history. So here what I'm showing is a plot of the fractional density perturbation in dark matter. This is dimensionless. It's delta rho over rho for dark matter. And this is shown for a single Fourier mode as a function of scale factor. So what does a density perturbation do during various cosmological eras? Well, while it's outside the horizon, nothing happens, it's flat. When it enters the horizon, it gets a kick. So these white areas here are radiation domination. So what this kick is, during radiation domination, the universe is expanding too fast, gravitational potentials decay. So what happens is things enter the horizon, they see the initial gravitational perturbation, they start flowing towards it, but then the gravitational potentials all decay. And so you're just left with this initial glide that very gradually slows down. So this initial kick you see, oh, we're going to flow towards the initial perturbations, but then those decay, and you're left with this very slow glide that gives you, during radiation domination, a logarithmic growth. So you have density perturbations growing logarithmically during radiation domination, but then during matter domination, the universe is now expanding less quickly, and so gravitational potentials have a chance to grow. And that means density perturbations have a chance to grow, it turns out, linearly during matter domination. So the standard cosmological history has no early matter-dominated era. If you enter the horizon early, you get a bump in growth, and then you grow logarithmically for quite some time before ultimately you hit A equality, and then structures really start to grow. So in a cosmology with an early matter-dominated era, you can see this is not a, this is a very log scale. This is a few decades, not too long, of matter domination, but linear growth is much faster than log growth. And so a mode that experiences some period of altered expansion history has a chance to rack up a lot of growth during this period. Then you go back to radiation domination, you have log growth again. You see there's a very big head start on structure formation in the presence of this epoch of early matter domination. And what this means is, so notice that I have plotted here deltas that go up from small numbers up to 1. This means fluctuations are as big as the average, and then even higher. You can separate Fourier modes in perturbation theory is linear. When modes get big, perturbation theory breaks down, the theory becomes nonlinear. This dashed line here is the critical density for collapse. That's when you have enough matter accumulated in a region that it becomes self-gravitating and the local region detaches from the Hubble flow. This critical density basically tells you when matter has collapsed to form a halo, a bound object that will then survive at least the homogeneous expansion. This is when you form structure. Now, this number is the critical density for collapse during matter domination, which is very well studied. This mode actually crosses the threshold quite early. It has experienced so much growth, it actually collapses during radiation domination, because during radiation domination, it's harder for potentials to grow. The critical density for collapse is higher. The process of collapse is both more complicated and less studied. But notice that here they're order 1. This is 1.686. This is roughly 2. So when delta becomes of order 1, that's when it collapses. That's when you form a halo. And those halos are going to be what we are ultimately interested in trying to see if we can grab onto. So now that this was showing what altered cosmology does for a single Fourier mode, but of course we have lots of Fourier modes. So showing what happens to the power spectrum of density fluctuations on a range of co-moving scales is what this slide is for. What's plotted here is this ratio of transfer functions. But you should understand this as describing the relative change in perturbation growth in a modified cosmology with an era of early matter domination compared to what happens in the standard cosmology where it's radiation domination all the way back to post-inflationary reheating. This plot is from work by Yue Zhang, who's one of the first ones to realize that relic radiation baths give you potentially modified structure growth when the decays are out of equilibrium with the standard model. So you can see here that there are some scales of interest. So there's no change for a while, because if you track back, we're going back in time as we go up in K. These are modes that enter earlier and earlier. Here is the end of the early matter-dominated era, when the field that is temporarily dominating the universe decays to standard model. So this corresponds to reheating. You can see that this is very close to BBN, and therefore reheating is this is about as low a scale as you can push it. Then there is more and more growth as we go back in time. These are modes that enter earlier and earlier in the early matter-dominated period, and so they have more and more time to grow during the period of altered expansion. The rise here goes like k to the fourth, which is a combination of the further back you go, you have more time to grow, and also this relates to the time when you enter the horizon size is also changing over this time. You put those two things together, you get this characteristic rise, goes like k to the fourth. But of course, this can't go on indefinitely. Something happens to cut this off. And this is part of where the dark particle physics it gets really interesting. And this is where the connection between the astrophysical observables and what we hope to learn about dark particle physics becomes really important, because exactly what happens to cut off this growth depends in detail on the microphysics of whatever is doing the domination of the universe and how it talks to dark matter. So on the particle physics side, if you want to understand where this cutoff comes from, that's an interesting calculation that depends in detail on your model. And on the astrophysical side, wherever this cutoff is tells you what the maximum value of this transfer function is, which means what is the scale that gets the most growth and how much growth does that get? And those are the things that are going to translate relatively directly into properties of the dark matter distribution itself that you would hope to see today, which I'll get to in more detail.
Jessie, can I just ask a question? Absolutely. I mean, I thought this matter power spectrum, the maximum was known quite well, right? The scale, I think, is around 300 megaparsecs.
Oh yeah, absolutely. Yeah. So this is the relative change compared to the standard cosmology. So these are also extremely small scales. So if I were talking about the peak of the overall matter power spectrum, it's like way over here.
Where is it, did you say?
Way over here. Oh, you can't even see it.
Oh, I see.
You can only see my cursor when it's on the white. Yeah, it's way.
Oh, I see. So the peak on the peak is all the way to the left. I see.
Yeah. So yeah, I've done two things. I've taken a ratio because this is just basically going to be 1 all the way out there. Because both cosmologies are the same.
I see. So this is just another bump that's later on past the peak in the matter power spectrum. Then.
Yes.
I see. Okay, thank you. Yep.
Yeah. No, thank you. That's very important, and that brings me in a very nice way to this. So let me see here. Yeah, this is important. We're talking about very small scales, and a nice dictionary between particle physics and scales is this set of lines here. So the scale that enters the horizon at the end of the early matter dominated era is the co-moving scale is equal to quantity AH. H is Hubble at reheating. Do a quick estimate and you can work out that's proportional to the reheating temperature, today's temperature over m Planck, so constants here. So horizon entry, scale is proportional to the reheating scale. There's a limit to how low you can push the reheating scale and still have successful Big Bang nucleosynthesis. And so there's a limit to how, how we can push K correspondingly. Now, K is useful for thinking about temperatures, but if you want to think about observations, what are the resulting structures that you see? You have to be able to convert a wave number to a halo mass. And so if you have a structure that is characterized by a co-moving wave number K, if that structure collapses, it's basically saying you're going to take all of the matter inside a sphere with the radius that corresponds to that co-moving wave number K. And that will be gravitationally bound into a structure. Given that this is a co-moving wave number, you can relate this to the dark matter density today. Notice that, if somebody asks me a question why I've put dark matter instead of all matter, I have an answer, but nobody asked the question, so I won't give the answer. Anyway, the mass goes like 1 on k cubed. So the fact that this is cubed and this is linear ends up being useful to understand how to map what halo masses you're sensitive to and observables up to what scales and therefore temperatures you can probe. So given that you can't push k too small without running into trouble with BBN, the kinds of structures on which we can modify structure formation are therefore limited to be sub-Earth mass size. So these are microhalos. These are extremely different from the kinds of small-scale dark matter halos that people are probing with, say, astrometry or lensing in galaxies, which are of order 10 to the 6, 10 to the 7 solar masses. This is a very different kind of structure. And so observable strategies are also very different. So yes, okay. So let me say a few words about the small scale cutoff again. So in the standard cosmology, modes grow logarithmically, and therefore, up until they hit this collapse threshold, then collapse. Okay, so in a cosmology that's this early radiation dominated, the standard cosmology, that means you have a lot of modes that have roughly the same amplitude, and therefore you have collapse occurring on a relatively large range of scales at roughly similar times. In cosmologies with early matter domination, the mode that's going to reach the collapse threshold first, these modes right near the peak of the transfer function. These are the ones that have a big head start on growth. And that means your very earliest epoch of structure formation is dominated by modes right around this scale. So understanding the microhalos that are born really then boils down to understanding what is the cutoff that ends this growth in dark matter density perturbations at the end of the EMDE on the high side. A variety of different kinds of particle physics that can give you cutoffs here. What's shown in this particular plot, this is a very sharp exponential cutoff. That arises from the tight coupling of dark matter to a relativistic species. It gives you a cutoff at the gene scale for that species. You can think of that as being essentially the dark matter is coupling to a species with a substantial pressure that becomes important at that scale. This is also the kind of thing that happens when you have a modulus where at some scale it has a quantum pressure that gives you a similar kind of gene scale. Other things that can happen is if dark matter after reheating, it has a relatively large thermal velocity, its free streaming can actually end up taking over whatever primordial cutoff you had and erasing it. And in some cases that can wipe out information about early clustering. And that's something we have to keep an eye on depending on the dark matter model. And something I've had a lot of fun playing with, if you have in this dark radiation bath, something that behaves very non-standard model-like, where you have interesting self-interactions of that species, then that can give you another new kind of cutoff that relates, again, the point of all these cutoffs is they give you a way to relate the particle physics of whatever is driving the modified expansion to the properties of the dark matter halos that are formed at a later time. A question, Raymond?
Yeah, so I have a question for the cutoff. So in these different cases, you would probably expect a different spectral shape if the cutoff is coming from different physical process. So does that mean we'll be able to use the spectral shape at that high K to actually know what physics in the dark sector actually sets the cutoff?
With enough data, hopefully, maybe it'll be hard. And I will have some slides later that will show what different shapes of cutoffs can do. But that is, I think, a very futuristic question.
I see. And are there other sources of cutoffs that are not coming from the dark sector?
So I think what we're ultimately interested in is the distribution of dark matter. So I would say, this one, the free streaming after reheating, is in some sense, it is probing the sort of late universe evolution of dark matter after reheating. And so that's somewhat different than this one and this one, which are directly probing the properties of the fluid that is doing the dominating. Most of the examples that I'm familiar with have a setup where it's a minimal setup, like you got the standard model and you got something else that's doing the fireworks. And so then your choices are either, well, it's in that fluid or it's in dark matter dynamics post reheating. That can come from something like dark matter, thermal interactions with the standard model. If dark matter interacts with the standard model, that will typically make it too hot to preserve these early density fluctuations. It has too much kinetic energy. It'll wipe them all out with free streaming.
I see. Thanks.
Can I ask also a question? The boost that you have is in the dark matter.
Yes.
Right. So, but the baryons are still delayed. They can't actually participate in this boost until you get past recombination. So
that's right. Yeah.
How is that taken into account, or what effect does that have?
Yeah, that's right. So these structures are small. They are, dark matter only, basically.
Okay.
Yeah.
Oh, okay. If it's the dark matter. So, but what about for galaxies? Is this not having an effect on structure of
yeah, basically, yeah. So the key is, not just galaxies, not even CMB. So what I'm talking about is pre-BBM. So these are scales that are, that are way smaller than any current observational test.
Okay.
So what distances?
Yeah, I'll talk later about some proposals to go after microstructure on these scales. I think they're promising but very futuristic.
But what distances are we talking about? This is sub parsec. I mean, or what distances are we talking about?
Good, yeah. So if you have one of these things, so like the physical size of these, not just the mass, but the physical size.
Yeah.
So if you have one of these things, it's like having an Earth, a tenth of an Earth mass spread out over the whole solar system.
Huh.
Now, depending on So they're very concentrated by the standard of NFW dark matter halos, but they're definitely not compact objects.
Okay.
Yeah. The earlier they form, the more dense they can be, but they're still halos. They're not compact objects.
I see. Okay, thanks.
So the point though is that for larger scale objects, having this early matter domination is, I guess, irrelevant because the scales are way outside that horizon and are not affected by whether you're matter dominated, radiation dominated. They're just doing whatever they do for those very large scales.
That's right.
Okay. Now I understand. Okay.
Yeah, and it's also worth saying, the scales that we're talking about are also substantially smaller than the typical building block size used in state-of-the-art cosmological simulations, where the dark matter particles are measured in units of solar masses still. So these are scales that are very subgrid for large-scale cosmological simulations.
Can I also ask a question? So do you always have a cutoff, or it also depends on the model whether you have a cutoff or not?
There's always a cutoff. It's not going to go on indefinitely. For one thing, right, this early matter dominated era is finite.
Okay, so what I assume is that if this matter dominated era. So that sector that dominates the universe in that era is completely different from the dark matter sector. Then I thought there might be no cutoff because before that, let's say that you have a radiation dominated era, then I thought that the spectral function will just become flat again. But maybe it is not correct.
So something will always cut this off, yeah?
Okay. So
So
I'm wondering if you assume some interaction between dark matter and the sector that dominates the universe in this early matter dominated era, or
yeah. So
okay.
Right. So if dark matter doesn't talk at all to whatever is dominating the universe, then this would transition possibly over into radiation domination again.
Yeah, then again, I think it will be flat, but yeah. I see.
And then
But you are saying the interaction.
Yeah, and so then in principle, same thing as in standard cosmology. If you don't specify a model for what dark matter is and where it came from, right, you also have this problem that the power spectrum just keeps growing at small scales in standard cosmology too. This radiation domination, something in some real model of dark matter. As soon as you commit to saying how dark matter got in the universe, there comes a cutoff along.
Sure. I just wanted to make sure that Yeah. Okay. Great. Thanks.
And actually, so I'm going to tell you about this cutoff with cannibals that I worked out because it's fun. It's fun particle physics, and it's a fun way to get the particle physics to talk to the cosmology in a way that gives you some very nice maps. So I'm going to tell you a couple things about what happens in a simple model here. This is a model where I've got two species, it's sort of a stick figure model. It could stand in for, say, pure glue theory plus a dark matter candidate. So we're going to think about a stripped down model that has just two particles. You have a particle, we'll call it scalar field phi, that has self interactions that are number changing. So this is a phi to the fourth theory with a cubic coupling here, as well as a quartic coupling here. And you can think about this as like, okay, I've got this one new particle, which is going to be my cannibal. This is going to be a species of particle that's in thermal equilibrium in the early universe for some time, then cools down, realizes it has a mass, dominates the universe for some time until it decays into standard model radiation and ends the early epoch of altered structure formation. Then, in addition to this cannibal, we've got a dark matter particle. And to start with, I'm going to show you what happens when you have a dark matter particle that doesn't directly talk to the cannibal through any particle interactions, just through gravity. And you'll still see a cutoff. Okay. All right. So if you have a particle that has number changing interactions that stay in equilibrium even after that particle becomes non-relativistic, then you have a very interesting period of time where the cannibal can change its number density to stay in equilibrium. That's what being in equilibrium means. It means the number density is determined only by the temperature. And so what happens is you have these processes where you have, say, 3 particles come in and only 2 leave. The particle is continuously changing its rest mass into kinetic energy, which lets us stay in thermal equilibrium for some time, even after its mass has become large compared to the temperature. This doesn't happen in the standard model because the standard model is always in equilibrium with relativistic species. Photon and neutrinos are there, and when particles become massive, as the universe cools down, they efficiently annihilate or decay into light species, and this issue never comes up. But it doesn't take an exotic kind of theory to realize cannibalism. It just takes a theory that has both number changing self interactions and a mass gap. So the lightest particle is massive. Again, glue balls or other mesons, say in various gauge theories, are extremely well motivated class of theories that can do this. but just plain phi to the fourth does it too. And the cross-section we're interested in is this cross-section for 3-to-2 interactions. The thermal average comes with V squared. This has, perhaps unfamiliarly, units of mass to the fifth, and it depends on the cubic and quartic interaction parameters in this way, which we can parameterize with a effective Cannibal coupling, specifically for the characterizing the strength of these number-changing self-interactions via alpha C. So think of this as some complicated combination of numbers, which is not large, and that's worth noting, times alpha C on m to the times m to the 5, alpha C cubed mass to the fifth. So what happens when you have this theory that continually heats itself up through these annihilations is a theory that doesn't cool down very quickly. So what I'm showing here is energy times A cubed normalized to mass to the fourth. So when the theory is matter, that is just energy density, co-moving energy density divided by in units of the mass, and that's just flat. This is where you see something behaving like radiation and diluting like 1 on A to the fourth. And then in between this region where this is set at temperature of 10 times the mass of the cannibal. So here it's relativistic. You see the energy density going like 1 on A to the fourth. Over here it's very non-relativistic and the cannibal interactions have frozen out and it's behaving like matter. In between, you have this period of cannibal evolution, which goes where the temperature basically drops logarithmically. And so the energy density scales like 1 on A cubed log A. And then this period here, this red line indicates when Maxwell-Boltzmann statistics, the red line indicates Maxwell-Boltzmann statistics. You can see that goes quite nicely. Ultimately, of course, these cannibal interactions, they can't keep going forever as the field gets more and more dilute, and eventually they freeze out. We characterize the freeze out by setting the number density squared times the cross section equal to Hubble. So when the interaction rate for these self interactions equals Hubble is when they freeze out. So here's this period of cannibalism shown in red. It's hard to make this very long. So it's typically about 1 to 3 decades. The ratio of scale factors that you can get between when it freezes out and this 10 times the mass here when we start depends on mass relatively weakly, depends on alpha only to the 2/3 power. So this roughly 2 decades typically, unless you really, really push the parameters of the theory. Now, difficulty cooling means that the velocities of the particles and therefore the pressure also changes fairly slowly. So showing here both the sound speed and the equation of state, W is P over rho. You can see this starts out radiation-like, ends up matter-like, but the thing to really pay attention to here is pressure goes like P squared, that for a particle that redshifts like 1 on A squared. And so for a particle that didn't have cannibal self-interactions with the pressures that it has out here, extrapolate that back without thinking about cannibals, just like the 1 on A squared evolution. You can see this would-be fluid, right? Running it forward now is cooling down very fast compared to how long it takes the cannibal fluid to get down that far. So basically what this is saying is the cannibal fluid throughout this period has way more pressure than you might expect. If it had just suddenly frozen out down here, it would cool down very fast. Okay. So other thing to pay attention to is the black and the blue here are the sound speed and equation of state parameter respectively for the evolution, including this freeze out. And you can see W starts to change right after freeze out. There's a factor of roughly 2 before C squared starts to really deviate from its equilibrium value. And then we'll see this roughly factor of 2 in the sound speed show up later. Okay. Then because the freeze out of the cannibal interactions and the decay of the cannibal field into the standard model are controlled by different Lagrangian parameters, there can be a potentially very lengthy period where the cannibal fluid basically behaves like matter. Gives you just a garden variety ENDE with potentially more thermal energy than you would naively expect. All right. So what happens to perturbations? What I'm plotting here, these 2 panels are showing as a function of scale factor starting at the temperature 10 times the cannibal mass and going through reheating. And so the top line shows a bunch of scales. This one is the horizon scale. So this slope is growing according to expectations for radiation domination. Then you see it start to bend when the cannibal field starts to notice that it's relativistic and the cannibal behavior starts to matter. Bends even more after freeze out when it behaves like matter, hangs out for a while, reheating, up, goes back to radiation domination. The other thing that I'm showing here is a gene scale. So again, a gene scale, for those of you who don't speak astro, which was me back when I was doing LHC physics for sure, is the mode that separates growing modes from oscillatory modes in a fluid. So this is basically characterizing the instability scale of a fluid to collapse. Sorry. So this you can work out for the cannibal perturbations is related to AH, the horizon size. It's got CS downstairs and it's got the equation of state here. And so you can plot that here. So it's growing, it starts bending, it bends more and more, and then it keeps growing up until the fluid loses its thermal equilibrium, sound speed growth, stays near its equilibrium mode for a while, and then it turns around, this is that factor of 2, and then it turns around and starts decreasing again after the cannibal drops out of equilibrium. So you can think about this as characterizing the importance of pressure in the cannibal fluid. It is quite large until cannibal interactions stop being able to heat the fluid up, after which it decays. So what happens for this mode here? It comes in, it enters the horizon, and I'm going to talk about perturbations for this mode here. So let's first focus on the red. That's the cannibal. That's the thing that's dominating the universe. So it's the thing that's going to drive the gravitational potentials. So it's flat while it's outside the horizon. It gets the kick when it enters. Then this mode here is inside the gene's horizon. I said gene's horizon separates oscillatory modes that feel the pressure support from collapsing modes that where pressure is not effective. So it's oscillating, and it keeps oscillating until finally the gene's horizon has decayed enough that this mode, that the pressure can no longer prevent this mode from collapsing. Now, then it finally starts to see the linear growth characteristic of matter domination, and it will grow until the cannibal fluid disappears. Now, the dark matter, flat, gets a boost. The dominant thing here, the thing that's controlling the gravitational potentials, is oscillating relatively quickly. There's no net potential here. So dark matter is completely flat. It's not even growing logarithmically, it's just flat, up until the cannibal perturbations start to grow, at which point dark matter finally says, oh, there's potentials here, I can fall into them, and its perturbations start to grow. Radiation is basically just along for the ride. So a couple assumptions: dark matter and cannibal are coupled only gravitationally, and the cannibal species is always dominant over the standard model radiation graph given time, which I don't think I will have. I will tell you what happens when you relax these assumptions.
So Jessie, can I ask a question about this cannibal?
Please.
So this cannibal is produced in the early universe after inflation. And then, so it has to couple to the inflaton, is that right? There's some.
Yeah, sure. Easiest way to populate this, to realize this kind of cosmology, is to have some period of asymmetric reheating. You've got an inflaton, it can talk to both standard model and to hidden sector, populates them with different energy densities.
I see. And then the lifetime is really long. So what sets the scale for the long lifetime? Because it has to decay, right?
It does have to decay, yeah.
So, so what sets the scale for that?
It depends on your model. You have to have the cannibal decay to the standard model in this minimal cosmology. So if you have a specific model of reheating, that will give you a lifetime. If your cannibal is composite, that is a very easy way to get long lifetimes.
I see. So you're imagining some higher dimension operator that this cannibal couples to the standard model, and there'll be some scale there in the denominator. I see. But you had more details of the models in your paper, is that right?
I mean, yeah, there are concrete models, but we didn't consider, we weren't very worried about working out a specific high scale model to populate this.
But there's no issues. You don't see any issues.
There's no issues. It is very easy to get the combination of populating two self-interacting sectors at different temperatures, keeping them out of equilibrium, and still having a acceptably long and acceptably short lifetime for one of the particles in a given sector. There's a lot of freedom in the kinds of Lagrangians you can write down. There's plenty to accommodate this kind of physics. Yeah.
Okay, thanks.
So ultimately, what we're interested in is understanding the cutoff. So we want to understand how different modes that enter at different times experience different growth in this scenario. And so the red mode here is one that enters relatively late. It only ever sees growth. This, as far as this mode is concerned, this looks like an early matter-dominated era because the funky sound speed produced by the cannibal dynamics is never important for this mode. So that gives you, something like this, and it gives you this red line here, where both the cannibal and the dark matter are basically behaving like heavy, non-relativistic, matter species, and therefore their perturbations look basically identical. They're right on top of each other. They're flat. They grow. It looks like early matter domination. This blue mode, on the other hand, is one that's very similar to the mode we showed on the previous slide. Enters the horizon, then enters the inside the gene's length, oscillates for some time before escaping. So you can see here, there's the cannibal oscillating, then finally grows, whereas the dark matter, hangs out, does basically nothing until the cannibal starts to cluster, at which point the dark matter eventually joins up with the cannibal. So the mode that's going to get, so this mode, this red mode, didn't enter early enough to get the full growth. This blue mode entered too early. Its growth got suppressed because oscillation is not growth. So the mode that gets the most growth is the one that enters early enough to get the full length of time inside the horizon, and therefore the most growth, without ever crossing the gene's length, in which case oscillations would suppress. And that is this black mode here. It just skims the gene's length, and therefore it realizes the most growth out of all the modes. So we can estimate the peak wave number by just asking about the maximum size of the gene's length, like so. So the scales we really care about are, when did it stop? When does this growth relative to the standard cosmology start? Where does it stop? How big does this get? And so we are now in a position where we can make some very simple, straightforward estimates for that. The amount of growth you get relative to the standard cosmology just depends on how long you had in between freeze out and reheating, which is something you can directly compute in terms of your Lagrangian parameters. And where this happens basically depends on how far there is between the time when the cannibals started to act heavy, what scale the mass of the particle started to matter up until when freeze-out happens. And that again is something you can just estimate very quickly, very simply in terms of Lagrangian parameters, and it gives you this parametric behavior here. And these are different parametrics. Okay, so in interest of time, I will just tell you that in this particular case, it turns out if you add a tight coupling, a particle interaction between cannibals and dark matter, you get exactly the same results for the quantities that you're likely to actually be able to access. You get some differences at very small scales. You still have to worry about cannibal self-interactions, even if cannibals freeze out before they come to dominate the universe. So let's now say some words about how we get from this transfer function to something that we can start to actually ask questions about in the late universe. Because ultimately we don't care about transfer functions, we care about microhalos. Now, the wave number, as I've said, sets a characteristic mass scale. Now, the peak height, how much early growth you got, determines the formation time. And that matters a lot for observational prospects because earlier forming halos are denser. Very roughly, the central concentration is proportional for halos that collapse during matter domination to the transfer function. And so the earlier you form, the denser you are. Denser is good because it makes you more visible and it makes you less vulnerable to disruption in the late universe. Now, connecting the very first forming microhalos, which are the ones that it's relatively easy to talk about in terms of what does a transfer function give you? It gives you a population of microhalos that form first. But those microhalos are not the same ones we see today. What we see today is the result of a lot of mergers and various evolution of those halos later. That step requires a lot of detailed modeling. And everything I'm going to say is based on some stick figure estimates, which are sufficient to say, this is potentially interesting and deserves further study. So the very first question you probably are thinking is, fine, you're talking about these very first forming microhalos, they're very small, they're going to go on and merge with a lot of other things, and there's going to be a lot of dynamics, they're going to get tidally disrupted all over the place. Did they even survive? The answer, as long as they formed early enough and are sufficiently concentrated, is probably. And I want to say this is probably, not a definitely yes or definitely no, because to answer these questions really rigorously would require simulations of these nonlinear dynamics that are capable of resolving these, sub-Earth mass structures inside galaxies, not as a computational problem that we just don't have the current tools to answer. So that's why I'm talking about estimates. This is also a place where it is useful to point out there's a substantial body of literature making estimates for a very similar kind of problem, which is about axion mini-clusters. Axion mini-clusters are objects that are born with order 1 density contrasts at relatively low temperatures, and therefore are often very similar in their properties to the kinds of pre-BBN microhalos that I'm talking about here. And in fact, this plot here is taken from this paper and was done for axion mini-clusters. So the result of a variety of estimates, including some of mine with these collaborators, is that an order 1 of these early forming microhalos are likely to survive inside Milky Way-like environments, albeit rather highly tidally stripped and not in the very dense galactic bulge environments. The most dangerous thing for survival is stellar encounters. And based on estimates of energy injection from stellar encounters, we found that as long as they form sufficiently early and are sufficiently concentrated, so formation of redshift roughly bigger than 250 in the Milky Way, we find that they are still persisting locally. And that is very similar conclusions to this estimate here. The other question you're asking is, yes, sure, but how are you ever going to see these? So here, my personal view of what we think we know about how to see these things is that the answer is probably, but more work is needed, and the observations are futuristic. There are three main observational avenues for pursuing these. In terms, perhaps the most well-developed is in the case where you are lucky enough that your dark matter has some annihilation cross-section into visible cosmic rays. This is a scenario where, you know, having a substantial fraction of your dark matter bound up in very dense structures compared to the standard scenario obviously gives you an enormous magnification of your cosmic ray dark matter annihilation signal, and you can have, you know, excellent detection prospects and excellent, if highly model dependent, constraints on your model. But having probes that depend only on the gravitational interactions of dark matter is obviously something that is applicable to a much broader range of theories and is highly interesting. And here there are really two ideas that I'm aware of. One of them is something that Catherine Zurich and her group has been studying extensively recently, and that is signals in pulsar timing arrays. And something that is somewhat less developed, but potentially very interesting, is cluster caustic microlensing. This is when a single star is fairly close to the caustic for being lensed by, you know, an entire galaxy cluster. So this, in this case, the signal is shown here. So this is the amount of magnification that you see. Now the star is basically moving, you know, through the caustic. You have this enormous magnification. This is, you know, time. If dark matter had no substructure, you would see the dashed line here, a smooth signal. It goes up, it has a blip, and then it moves away from the caustic and the signal dies. In this case, the lumpiness that would be caused by structure, this very small substructure, is the signal. It is these, you know, blips here in the light curve. And then looking at the statistical properties of that light curve will tell you about the power distribution of the mass in the lensing cluster. So this plot was worked out by my collaborators as a very rough estimate of the sensitivity based on one of the observations of this kind of cluster caustic microlensing by the Hubble telescope. And the width of these curves corresponds to the assumed fraction of dark matter that is bound up into microstructure. You can see the range of scales that is interesting for potential signals. This region is where, you know, in this rough estimate, we think we can see things. This range is about right to be able to probe sub-Earth mass microhalos. It is worth saying, Hubble Space Telescope has seen a couple of these cluster caustic microlensing events. None of them have been observed on sufficiently long timescales to give you the kind of integrated sensitivity you would need to resolve this effect and be able to make measurements. And to the best of my knowledge, there's not been the kind of careful work dedicated to seeing whether this kind of signal is visible over all of the experimental systematics. I think would be extremely interesting to push. I'm aware of the time, and I'm worried about making all the high points. So let me show you quickly. This relates to Raymond's question earlier about how various cutoffs, various different predictions for various peak shapes from different particle models affect signals. So you can see rise slope is easier to see, but cutoff can give you signals on small scales. If you had enough resolution on small scales, you could in principle detect the differences between these, but the very first thing you'd want to see is this. Okay. So here are a couple different simple scenarios for structure formation. Here is a early matter domination like peak with a sharp cutoff. Here's one with a going over to radiation domination sort of plateau. And here is what we think they would do in possible cluster caustic microlensing scenarios. So so part of the reason why lensing by gravitational clusters as opposed to pulsar timing might be a robust way to go, or an attractive way to go after these kinds of small scale structure formation, is that pulsar timing arrays are based entirely in the Milky Way. And so they are probing the kinds of structures that can survive inside the fairly hostile environment of the Milky Way for dark matter substructure. And we estimate that they're limited to probing dark matter halos that formed microhalos that formed prior to redshifts of about 250. On the other hand, for lensing by whole galaxy clusters include an awful lot of dark matter that is not inside these very dense galactic environments, and therefore you are less vulnerable to the kinds of late redshift disruption of these structures. These contours here are showing you how the redshift of formation relates to the scale density, the equivalently concentration. So the higher you go here, the more concentrated you are. And the lower you go here, the less mass you have. And so a typical 1 sigma density fluctuation would give you signals along in here, possibly visible. Rarer fluctuations born out of the same field would give you signals up here. And so these are, I would say, our estimates are this is potentially interesting and worth pushing further. Is it observable? We have not shown that. There's been no careful study of systematics, and making these observations would require extended time observations of systems with possibly James Webb Telescope or Hubble. All right, so I recognize the time is getting quite late. Let me then just conclude. There are a lot of interesting particle physics things that can go on and modify the expansion history of the universe before Big Bang nucleosynthesis. Knowing more about the early universe expansion history can help us understand the ingredients of our universe at early times and help us shed light on interesting puzzles about the particle physics of our universe. I've had fun exploring this with early cannibal-dominated eras, which enable you to make a very sharp map between the Lagrangian of the particle and the astrophysical scales that control the behavior of the early universe. And part of why this is interesting is gives us some ways to explore looking for the signals of this altered evolution in the granularity of the dark matter distribution on very small scales. Futuristic, but very cool. Thank you for your attention. Sorry for running long.
Thank you. Let's thank the speaker for the very nice talk.
So I had a question just related to this early matter domination. Sometimes people invoke an early matter domination to explain the change in Hubble. Is that possible? And can you combine the two? And does it give a signal with a bump in the matter power spectrum as well that can be observable?
Yeah, yeah. I mean, it's very hard. You have to somehow figure out, if you want to play with the expansion history of the universe in a way to fix up the Hubble tension, you basically have to figure out a way to do it right around the around recombination. And you need to do it in a way that doesn't inject entropy.
so your scenario wouldn't work if I put it near recombination?
No.
Oh, so it has to be much earlier. I mean, the way you're getting away with it, because you're much earlier, right?
Yeah, that's right. I mean, basically, you can get away with murder before BBN.
I see.
But then, yeah, we're trying to figure out how to. Ultimately, of course, the goal is to figure out whether there are ways to, find the murderer. With new observables. Yeah.
I see.
Yeah, I mean, the killer for a lot of these late time scenarios is the entropy injection that comes along with it. If you have a scenario where whatever is, so if you have some epoch of altered expansion history, something has to change in order to get you back onto the standard expansion history. And most of the time, most of the models that you can figure out how to do that, you have something that is massive and then you have to get rid of it so it has to decay, or somehow its equation of state has to dramatically change.
Mm-hmm. But
Anything that involves a decay is really dangerous.
I see, but if I was to solve the Hubble tension, what would it correspond to scales in the matter power spectrum?
So if you want something happening around, well, good. Yeah, you want something happening around A equality to make that happen. Those are roughly the scales that are towards the small side of the CMB.
Oh, okay.
Yeah, that's the easiest way to see it, because CMB and A equality are roughly the same.
See.
So, I mean, if you want something to decay without injecting entropy into the visible universe, then the easiest thing you can do is have it go into dark radiation, but then you have to figure out how to make sure you don't get too much dark radiation. And if you're doing something relatively late, that is also a problem because you're limited in terms of how much N effective you can afford.
Mm-hmm.
Yeah. So then you're really talking about something where you have to do something very clever to get rid of it. And I want to put in a bit of advertisement for something in particular, Raymond and collaborators. So with me and Nico Fernandez and some other people, we're looking at Kinnation. The nice thing about Kinnation is you don't have to worry about getting it to go below radiation. It does that just by redshift. And that's a nice way that you can have an epoch of modified cosmological history without having an entropy generating issue at the changeover.
I see.
So that's very attractive, but there are relatively few models, relatively few nice models of Kinnation, and the Axion Kinnation model worked out by Raymond and collaborators is really the only one that I know of. But for all this stuff, you should ask Raymond because he's there and he knows it.
Right, yeah, thanks. Yeah.
Jessie, thanks for the nice talk, and thanks for using particle physics language from time to time. Helped me a lot. But my question are very naive. But when you say you form those microhalos, are they all of the dark matter or just a component of the dark matter?
Yeah. So these halos are tiny. They're smaller than the baryon gene's length. They only contain dark matter. Yeah.
I mean, they are all made of dark matter, but do they saturate the whole? All of the microhalos, are they make up?
You're asking what fraction of dark matter is contained? Yeah, good. So it starts out as order 1. It starts out as 1, right? The first things that collapse are these microhalos. And at that point, all dark matter is in microhalos, basically. And then slowly you build up bigger things. And then it becomes a detailed question. How much is still in microhalos versus how many microhalos have sort of lost their identity as they merge into bigger things. So it is not, there are not very sharp answers to that because it requires, to answer that question really properly requires running simulations with insane resolution compared to what we currently have. It seems quite probable that an order 1 fraction is, but exactly what that order 1 is, I can't tell you exactly.
But is that sensitive to the assumption that I don't inject any self-interaction between dark matter? Or in the sense that if I turn on any self-interaction, do all my microhalo, most of my microhalo are gone?
No, I don't think so. We know that interactions between dark matter cannot be in the late universe too strong.
Sure.
And so I think that.
But here your one instruction is they don't interact with each other beyond gravity for this dark matter.
Yeah, certainly I'm not imagining that. There are still some self-interactions in this theory, but their interactions are cosmologically not important after the cannibal interactions freeze out.
Another question I have is, you in your early discussion about this cutoff, right? Of course, the cutoff shape and the height depend on your underlying new physics that about this matter domination. But I still wonder what's the freedom, roughly within reasonable model, how much I can change that cutoff behavior.
Yeah,
and how
good.
they impact my later discussion on the micro halos. It seems like I don't have too much freedom, and it wouldn't affect the micro halo dynamics much. But that's my guess. But can you tell me?
Yeah. So something that is important and relatively universal, and that I didn't really touch on, is that if you let the early matter dominated era go on too long, then you actually end up with your halos collapsing during the early matter dominated era itself. And that means they're dominantly composed of the metastable thing rather than dark matter. And that means that when this thing decays into energetic radiation, it just blows itself apart. So there are some relatively model independent limits on what the dark matter halos, how dense they can be. And that just comes from, you can't let the, if you want to see signatures in the dark matter halos today, there's a limit to how big the peak can get before you start entering the regime where early structure, catastrophically early structure formation ends up wiping out the signal. But that's independent of the dark matter dynamics. I think you're asking a question about how dark matter itself interacts and whether that changes structure. It's an interesting question, and it is not actually one we asked.
Yeah, I think I actually understand that part. I was asking within your reasonable modeling about the dynamics determine this cutoff slope and peak in this in your earlier plot. What's the range I can think about the model freedom roughly? Slope change plus the.
I see here. Yeah.
Yeah.
Yeah. Good. So for each one of these rise slopes, we have a model. For the peak fall slopes, there are not as many different models that I know of. These sharp exponentials, which we very crudely model here, are when you have free streaming, Jean's length. That's sort of the most common one. This plateau is a crude model of, let's go back over to radiation domination. So whatever cutoff is pushed to very small scales. And then the cannibal cutoff is a 1 on k squared cutoff. That's this one here. We don't actually have a model that gives this one. It's just a nice intermediate that fits on the plot. For all of these, there's actually some cosmological scenario that gives those. Like if you have direct inflationary production of some things, you have not adiabatic power spectra, but isoperpetual spectra with these very gradual rises.
Yeah, I think, thanks. I just want to get a rough idea about the lot variation. This helps me understand. Thanks.
So, this is, being at the level where we could look at, say, micro lensing and say, oh, what's this slope? Let's distinguish between different particle models of what's going on in the early universe. It's going to be an extremely long time before we ever get there. So it's interesting to know, what these do, but the biggest thing we're going to want to see is like, oh, do we see any signal here at all? And it's going to be in the short term much more useful for constraining what we know about deviations from radiation domination than actually letting us discover.
Yeah, thanks.
So let's say if you see a signal in the power spectrum, how would you be able to distinguish whether this sector is a completely dark path or is doing similar physics in our path?
What do you mean by similar physics in our path?
For example, so you have different ways to have the cutoff after the rise of the power spectrum because of the enhancement of the matter power spectrum. So how much of it has to rely on the fact that this thermal path is in the dark sector that's completely hidden from the center model, or can the same analysis apply if for example, cannibalism is happening in our own
good. So In the particle models that I've been talking about, you really have to have the dark bath and the standard model bath be out of equilibrium, because otherwise you would never have a chance for these out of equilibrium species to actually dominate the energy density of the universe. So the out of equilibrium is critical. You don't get cannibalism unless you're out of equilibrium with relativistic species, for instance.
And you cannot assume the matter domination coming from completely different sector, like inflaton or moduli.
Oh, sure, you can. So if I have a modulus, right, that's another way to get out of equilibrium. Yeah.
I see. I see. Okay, yeah, that makes sense. Thanks. Do you have any more questions from the audience? Okay, if not, then let's thank Jessie again.
Yeah, thanks so much, Jessie, for a nice talk. And,
Thank you for listening. It's nice to see you guys. I wish I could. I what's the phrase? Next year in Jerusalem. Next year at Snow. I don't know.